Today presentation I will talk about integration a solar cell, integration and fire antenna inside a solar cell panel for small satellite space mission. This work it's a part of a mission funded by 𝗖ًcie, and it's carried out after that with the Heritwat University and the University of Edinburgh as I'm a PhD student there, and also for 𝗨𝘀 Orbital. Before getting to explain and going too deep inside the antenna and the stuff, I will just give you a quickly overview about what this presentation will talk about. I will basically give an introduction about the work and the mission and the motivation of this work. Then after that, I will move to the solar panel key feature and how we can integrate the antenna design. And in the antenna design section, I will mention at the first some example or let's say literature review, state of art about end-fire antenna before I go deep inside our design and mentioning the challenges that we are facing right now. Then I will finish with some conclusion. Basically, what is the purpose of this work? 𝗨𝘀 Orbit want to increase the mission in their new satellite, the Unicore 2, and by increasing the mission of this inside one satellite, and their interest is the Earth observation surface, and which is adding optical payload, which is will take, as we can see here in this picture, most of the space inside this Pico satellite. And at the first look to this cube satellite, like you can say that where is the antenna will be fit. And I will tell you how we manage in the upcoming slide. Like we can see here that the satellite or the solar cell have plenty of space inside it. And thinking or like imagining get inside to design an antenna and integrate it inside the solar panel absolutely will have some advantage, and I will not say disadvantage, I will say challenges. So the advantage that we will not increase the weight, the and also the space is there, just we need to think and how to implement. And this one of the advantage, it will increase the novelty is a state of art working. And some of the challenges of the mission, if it's a low frequency due to the wavelength that the antenna have a limited in dimension. And when you work in the solar cell panels, you have a certain dimensions that I will talk about in the upcoming slides. And also transparency conductors material reduce the efficiency of the antenna. And as we can see here in this picture at the bottom, you can see the antenna. And in the EU mission, we will design an end-fire radiation, and in the ISL mission, it was implementing a board-side radiation. To give the ways or the techniques to implement an antenna, we have the first, the metallic grid. And as we can see, there is two reference. The first one here, you can see the feeder here, and also, as you can see, the grid of the metallic grid that will radiate toward the board side. And the second technique is transparent conductors, and this have two ways. The first way by the nanoweb, and the second way by the transparent conductive oxides. And dealing with the transparency conductor, you need to have a weight. You need to have that if you increase the transparency, it will have affect the conductivity of your antenna, and your antenna might not reach the requirement. And as you can see here in the bottom, the picture of the transparency conductor antennas, that so the useful of this, that letting the cell get the sunlight and produce the energy for the satellite. And as you can see here in this picture, there is a two board side radiation mission, and the bottom one, it's an antenna that's using the metallic grid, and this work being done in Edinburgh City, so it's in Hertwat University and also in the University of Edinburgh to achieve such a kind of this antenna. Moving to any mission, or moving to this slide, for any mission of a cube satellite or any satellite, you have a specification. You need to meet these requirements. I will explain first that the behavior of the pico satellite or the antenna, as you can see here, when the satellite facing the earth, you will have the connection and the link is okay. But when your satellite pointing other side than the earth, you will not have the connection. And for the specification to design for this mission, the frequency, the operation frequency need to be 2.4 gigahertz with a bandwidth at least 10 megahertz, and also again between the 3 dBi if the antenna give a circular polarization, or a 5 dBi when the antenna give the linear polarization. And these specification for the gain, it does not include the losses in the conductor, as anyone know, for the RF side or the antenna side, the connectors of that providing the energy, it might sometimes lose some of the energy. And also one of the most important requirements, that the antenna need to be weight, or the mass of the antenna, less than 10 grams. And here in the substrate that we will use the glass, the borosilicate glass of the solar cell, and this have a certain dimension that here it's, I think it's, you can see it better, that we have a width of 53 millimeter and a length of 43 millimeter in the top view, as you can see. And also in the side view, we have a thickness of 0.2, and this thickness, it's give us one of the limitation that we need to design our antenna with using a substrate. It's the glass of the solar cell antenna with permittivity of 4.6. Moving to the antenna design part, and as I mentioned before, I will explain at the first some of state of art or some example of end-fire pattern antenna. And as you can see here, the first on the left, the first example, those people have designed an antenna that radiate, as you can see here, in the toward the end fire pattern, and it's working in 2.45 with nearly 2 dBi as a gain. And in the middle here, it's another example. It's trying to design a Yagi array antenna, and those people achieve a quasi end fire antenna, and with the working our operation frequency, as we can see here, it's 1.5. And also the third or the last example that I will present here about a group. Also, they want to design a printed dipole, reflected, as you can see here, reflected the signal toward the end fire. And in the radiation pattern, we can see that they achieve a good results by 5.4 gain dBi, and also their antenna working in 4.7 gigahertz. Here it's our antenna, and as you can see here, this is the solar panel with our antenna integrated on it, and this is on one side, the top side, and as you can see here for our antenna, we have the top view, and the side view, and also the bottom view, and you can see the glass of the solar panel, and you can see those three. It's the directors that radiate or like make the antenna excite toward the end fire. And also, as you can see here, there is a minimizing a dipole that I will explain it. It's the driven element, and at the here it will give us the 50 ohm microstrip input. We can see here about what I explained, because we have some limitation. The non-minimizer Yagi antenna, it's need to be of a 53 as a length and a width 51.5. And because of this limitation, we try to came up with a minimizing Yagi antenna using this kind of changing inside the structure. And moving to, after we minimize these, I will explain some of the results that we came up with. In the bottom here, we achieve a 5.02 as a gain, and this is one of the specification of this mission. And as you can see here, it's toward the end fire direction to the 90 degree, and this is one of the beautiful things that we're happy to achieve. And the return loss that this antenna matching the 2.4 gig as operating frequency. And as you can see here in this right up graph, you can see that the realized gain, and to whom those people that don't know what is the realized gain, it's show you where your antenna that really match, and comparing between the return loss here and the realized gain, we can see that 2.4 give us the best performance, and it will be 5.02 giga dBi. I'm sorry. And this antenna give us a bandwidth of 143 megahertz, and also have a reflection coefficient and a matching with a minus 15.47. Moving to explain what is the challenges that will that we need to take think about, and to optimize and get a better response. We realize that in the solar cell, as you can see here in the up picture, that have a continuous ground, and this affecting the performance of the end fire pattern and of our antenna pattern. We can mention some possible solutions. It's by increase the glass of the solar panels. The material, this will affect by increasing it, increase the thickness. It will have a distance between the top or the acting parameter of our antenna comparing to the continuous ground. And the other thing will be, it's by exploring the quasi end fire. It's by changing the ways and see if we achieve a quasi end fire, so the direction of the pattern will not be at a 90, maybe will be at 60 or 70 degree. And this is something might give us a better performance for the antenna. To sum up with, to give a conclusion that EU mission payload taking most of the space, and because of that, antenna integration to the solar panel needed. And the dimensions, the limitation in dimension when we designing for low frequencies, such as in this mission, it's 2.4 gigahertz. It's need to think about good techniques, and also the continuous ground. It's one of the challenges that limitation implementation for radiation toward the end fire direction. Possible solution, as I mentioned, thicker layer of the borosilicate glasses may necessary to avoid the effect of the continuous ground. In the future work, absolutely, we will continue an investigation how we avoid the continuous ground, and how we adapt better performance. And this might be by differ or making the frequency reach to the X-band area. So at 8 gigahertz might have a better performance, and also simulate and see the effectiveness of the satellite platform, and also what will affect in the design, because sometimes you can achieve a better pattern, a good results, but when you integrated in the satellite, you might see some effectiveness in your signals. And this is the end, and thank you so much for listening.